So in this example, we are going to learn how to do heat balance calculations in FactSage. They're very useful when considering different industrial processes. For example, they can help us to calculate the energy input to raise the temperature of a material from T1 to T2. The vice versa is also true. They can also tell us how much heat should be taken out from a material to cool it from T2 to T1. Furthermore, they are very important in different processes like alloying because they tell us how much heat is evolved during a chemical reaction. And when we balance it with how much heat is lost from the furnace, we can actually calculate how much heat do we put in or how much heat do we take out from the furnace for temperature control in a process. So in this example, we'll perform two calculations. The first is alloying of manganese in liquid steel, and the second is cooling of MgAZ31 alloy from a higher temperature to a lower temperature. So in the first calculation, we are adding a ferromanganese master alloy at 25 degrees Celsius to liquid steel at 1600 degrees Celsius. So we'll perform this calculation in the equilibrium module of FactSage. So the first thing that we want to do is we want to make streams of both the solutions, so of the alloy as well as of the liquid. So first we'll select the database. We need to select FS Steel database for this calculation, and we are adding manganese and iron. So it's 65% manganese and 35% iron. So 65, 35, and we'll just do a equilibrium calculation. We don't need to select the initial conditions to save the stream file. We'll just select all the solutions. We'll also select pure solids and then we'll calculate. So as you can see in this calculation that we actually have two solutions that form in the master alloy. So we'll save both of them, which is the input alloy that we are adding to the liquid steel. So to save the stream, we'll go to output, stream file, save stream file, save solutions. And what we want to do is we want to save all solutions because we are adding the complete alloy that will form at 25 degrees and not just one of these solutions. So let's give it a name. So uh, FEMN at 25. Okay, okay, and then we'll make a stream for the steel at 1600 degrees. So we'll go to the input window, clear the system. We'll keep the same databases, that is FS steel, and then we'll add iron, aluminium, and carbon. So aluminum is 1 and carbon is 0.8. And we can, and because the total mass is 100 grams, because we are putting it in terms of mass percentages, so we can just put question mark 100. So FactSage then balances out the mass of Fe, considering that the total mass of all the reactants equals to 100. So again, we don't need initial conditions. We'll select all stable solutions. We'll select all solutions, and the equilibrium will calculate the stable solutions. This time the temperature is 1600 degrees. So we'll do 1600 and then we'll do a calculation. So at 1600 degrees, as you can see that we are only forming the liquid. So we'll save the liquid stream now. So stream file, save stream file, select save solutions and just the liquid one. So we are actually forming only liquid number one. The liquid number two is 0 grams. So that is why we are saving liquid number one. So over here we have Fe liquid, Fe liquid, that's a liquid solution. Okay. So So now that we have made the stream files, now we can do the heat balance calculation. So now to perform the heat balance calculation, we'll return to the input window of the equilibrium module. And what we're going to do is we're going to insert both of the streams that we made previously in the input window. So for that, we'll go to edit, mixture and streams, import a stream, and we're going to import both of the streams that we made. So the first is the ferromanganese alloy, and the second one is the liquid steel at 1600 degrees. So let's input this. And over here it says in quantity 100%. So the original stream that we made was 100 G. So there's 100 G of the liquid steel and 100 G of the master alloy. So over here I'm going to replace 100% with A because we want to add different values of the master alloy and see its effect on the temperature in this calculation. Because we are doing because we want to know the final temperature and we are going to do a heat balance calculation. So we need to select initial conditions when we are doing this calculation. So go next, and now we'll just select all solutions. We'll select the solids, and we are going to leave this field of temperature blank because we want to calculate the final temperature. But what we are going to do is we are going to impose adiabatic conditions over here. So delta Hg is equal to 0. So if we know the heat loss from the furnace for the duration of the process, then we can also enter that heat loss over here. We are going to vary the input amount of master alloy, let's say from 0 to 3 to 0.1, which is the interval of the calculation, and then we are just going to calculate. And this is the result that we get. And now what we want to do is we want to plot these results. So let's do that. So to plot, simply go to output, plot, plot results, and then we'll select the axis. So on the y-axis we want temperature in degrees Celsius, and on the x-axis we want alpha, which is the amount of ferromanganese alloy that we have added to liquid steel. So it varies from 0 to 3 grams. Just click refresh, just in case, and then OK. And now we are going to plot. So as you can see that when no ferromanganese alloy is added, that is when alpha is equal to 0, then the temperature is 1600 degrees, which was the original temperature of the liquid steel. And when alpha is equal to 3, which is when 3 grams of ferromanganese master alloy has been added, then the temperature has actually reduced to 50, is to around 1552.5 degrees. So this is the heat balance calculation for the alloying application. So the second calculation that we are going to do is cooling an AZ91 alloy from 600 degrees to 300 degrees. So for that we'll first again make a stream of AZ91 alloy at 600 degrees. So we'll go to the input window quickly, and this time we'll select a different database. So we'll select the FT-Lite database for this calculation. So okay, first I'll clear the system, and I'll keep the FT-Lite database selected, and we have Mg AZ91. So magnesium, aluminium, and zinc. And again, because we are making the initial stream, we want to deselect the initial conditions. So as it says in 91, so 9 here, 1 here, and again we'll balance it out with 100 grams of total alloy. So next, the temperature now is 600 degrees. We want to leave this field blank, otherwise Praxis won't be able to do any calculation. We'll select all solutions, pure solids, and then we'll calculate again. So as you can see that we are again forming only one solution, which is liquid. So we are going to save this liquid solution as a stream file. So stream file, stream file, save solutions, and we'll save the liquid. So again, we are only forming liquid number 1. Liquid number 2 is 0 grams. So that's why we are saving just that. So we'll name it as AZ91 at 600. And then we're just going to save it. And now for the cooling calculation, we'll again go to the input window, and this time we are going to input the stream that we just saved. So we'll keep the FT-Lite database. We'll go to edit, mixtures and streams, import a mixture, and we're going to import the AZ91 stream. Again, we're going to select initial conditions because we are cooling from 600 degrees. The quantity will be 100%, and this time we actually want to calculate the heat that is evolved when we are cooling it from 600 to 300. So let's say we are cooling two different steps, so 600 to 300 at an interval of every 10 degrees. We'll select all the solutions again, pure solids, and then we'll calculate. And now what we can do is we can actually plot the amount of heat that is evolved from the alloy when we are cooling it from 600 degrees to different temperatures, and where the final temperature is 300 degrees. So we'll plot results. We'll select the axis. So the y-axis this time is going to be delta H. The x-axis is going to be temperature. Do a refresh. Okay. And then we'll plot. So as you can see that when the material is at 600 degrees, delta H is 0, so heat evolved is 0. And as we are cooling it to 300 degrees, we have more and more amount of heat that is evolved. We can also see the phases that are forming at different temperatures during this cooling calculation. So for that, we'll again go to output, plot results, axis. The y variable this time is going to be gram, and x variable will again be temperature. So okay, select. And what we want to do is we want to select all stable phases because we want to see what all phases are forming during our cooling calculation. So select all stable phases, okay, and then plot. So as you can see, we have the liquid phase, we have the A3 phase over here, and we have the A12 phase over here. So A3 phase is actually the primary HCP phase, and A12 phase is the CBCC phase. You can see that over here. So A3 is HCP A3, and A12 is the CBCC phase. So these are the phases that we are forming during the cooling of MgAZ31 alloy from 600 degrees to 300 degrees.